how to maybe for some of these changes. We'll talk also very briefly about some of our plans for new state plane coordinate systems to go along with the new datums. So the National Spatial Reference Agencies define and maintain and provide access to the National Spatial Reference System, and you can see both graphically and in writing sort of what the NSRS is comprised of. Essentially, it's the coordinates, latitudes or horizontal coordinates and heights for our nation, but also scale, gravity, and orientation. These are also part of defining physical aspects of our datums. But as we move more and more into the time, especially when we're talking about using space-based technologies for positioning, that is to say GPS, GLONASS, other space-based satellite systems, and the fact that we've been tracking a lot of stations in this manner over quite a long time. The other part of the NSRS is that we really need to start to look at how these quantities change over time. And we can see definitely that they do change very systematically. Plate tectonics, we'll look at sort of what that looks like. But also there's quite a few examples of local motions, whether it be subsidence in Louisiana, whether it be uplift in the Northeast. There's a lot of local motions as well that aren't accounted for in our datums. So a really brief history of NAD83. Originally realized in consisted almost entirely of classical observations, that's meaning line of sight, triangulation, long measured baselines, a lot of work done from mountaintops and towers. Then we moved into sort of the space-based technologies, right? GPS, where we started primarily with geodetic networks, high-accuracy reference networks. That's what we call them here in the East, HARNs. Mostly done in the 90s, based on GPS observations, but all of the old classical stations were adjusted to the GPS. Then in 2007, we had a national readjustment of NAD83. Time ever, a simultaneous adjustment of all the GPS across the entire country. So the HARNs were a quilt of networks, regional networks that were sort of loosely tied together. But this project in 2007 actually was that one nationwide simultaneous adjustment that really sort of brought everything together. And then in 2011, we have yet another realization of NAD83, and this one, its purpose was essentially to keep it consistent with operating GPS reference stations, or our core stations. So why have we made these changes over the time? And I think it's important to just get a brief history of one place. Some I think will be very obvious, others maybe not quite so much. So NAD87 rather was an old system, and it worked quite well during the period that it was used. Observations were being done classically, right? So line of sight type observations done on fairly local scale, and the NAD27 control network worked well for those who were utilizing it. And then an NAD83 came along in '86, and in many ways that, although there were a number of underlying reasons, but from a practical standpoint, one of the reasons that 83 was important was because in the late 70s and 80s, people who were doing positioning started to use lasers or EDMs. And now for the first time, we could measure 10, 20, 30 miles, sometimes even, in one distance, where we weren't able to do that accurately with triangulation, but to be able to measure a distance very directly. So the coordinate system didn't support it. so long, and that supported that type of operations. And then the 90s, of course, GPS came on the forefront, and now our network didn't support the type of didn't support the accuracies that one could achieve with GPS. Now GPS is not a line of sight technology. We can go 40, 50, 60, 100 miles. And whether I can see from point A to point B doesn't matter. GPS still allows us to measure. Now we're really starting to see that they support that type of technology. And then in 2007, we removed this long-standing relationship with the CORS network, NGS's continuously operating reference stations. So we did this simultaneous relative to the CORS 11. We updated the CORS coordinates, so we needed to update the rest of the network to keep it consistent with the CORS. So along with all these changes, we've also had changes in the accuracies, both on a local level, meaning basically from one point that I can see to another point that I can see, to a network accuracy, which would mean in the early NAD83 days and NAD20, what's my level of accuracy continentally, so from East Coast to West Coast. And today, relative to the newer realizations of NAD83, it's how well the stations that we're positioning agree with the CORS network, which are the control network that we're using to control those surveys. So we can see over time that the local accuracy hasn't changed significantly, other than in the way that we represent it. We used to represent it in a 1 part per 100,000 type statement, which is great for surveyors who are running traverses, but for the GIS and other positioning.
Dan?
Yes.
I mean, it seems your presentation at a latent.
Hang on a second. Let me try. Give me a minute. I'm going to into it and see if that works any better. Can I see this? Come on.
No, you're ordering.
I don't. I can't hear you, Colin, for some reason. So I hear a little bit from you, but not the rest. You put something in the chat box so I can see what's going on. There we go.
The audio on the computer is dancing, or there's a bit of.
So it looks like the audio is working for some people, but not working for others. Yeah, I agree. Colin's audio is not fine. Can the audience? I assume the audience can hear me. Can the audience see my presentation okay? If somebody could answer and see the presentation. So I'm seeing people saying yes and yes. Okay, so I think the problem is, oh, audio's terrible. Yeah, I'm on computer audio right now. All right, I'm going to try to keep going, and if we have to, Colin, I'll be happy to do this again if folks don't get it. But it looks like quite a few people can hear me and see me okay. All right, let me just go ahead and see if I can keep going with this. Okay, so I should be sharing my screen now. Everybody can see my screen, is that correct? Okay. All right, let me keep going with this then. I apologize for the problems. Let's see what I want to do. Here we go. Okay. Yeah, so as I was saying, this 1 part to 100,000 type statement worked well for surveyors who were doing traverse, but for other positioning professionals, it doesn't make much sense. If I put a dot on a screen and it's 1 part in 100,000, you know, you say great relative to what, right? Relative to a core station that's 100 kilometers away, or relative to the other control station that's 50 feet away. So we've changed how we represent accuracies now in a more absolute sense, with a plus or minus certain number of centimeters at a 95% confidence level. So what do we use in New York? Oh, maybe you use NAD27, and if you do, that's okay. I mean, there's a need for being able to display historic data, but more than likely, folks are using NAD83, right? Latitude, longitude, or state plane coordinates. But if so, which one? Understand that there have been a number of different realizations of NAD83. Right, going back from the original realization, NAD83 86, up to today, NAD83 2011, EPIC 2010, and all of these coordinates are different. So the takeaway from this is, if you're creating data or representing data, it's important to be very specific about what that coordinate system is. Right, saying it's tied to NAD83 is not good enough, right? We need to tell a little bit more about that. And I endorsed saying as much as possible. It's NAD83 cores 96, EPIC 2002. I did it using the New York State real-time network. I did it on this date using this equipment. So as someone who does surveying work, it's important for us, so I can go out and try to recreate or tie into someone else's data. If I'm a GIS practitioner, it's important because I know I have an inherent understanding of the accuracy or the intended accuracy of that data based on the methodologies that were used. Right? I mean, I could treat 2011 coordinate, but that doesn't tell you how accurate it is. Right? If I could have done that with a traverse using a total state, done it using the real-time network, or I could have done it using NGS's positioning user system. Each one has its own inherent accuracies associated with it. Whether you make the statement correctly or not, some folks will say that they're tied to WGS84, and that's probably not into the intricacies of that statement. But if you truly were using WGS84, there's the other as to which one. There've been a number of different realizations of WGS84. The differences on the NAD83 side might be up to half, maybe 3/4 of a meter, right? From one realization of NAD83 to another realization of NAD83. WGS84, from the earliest to where we are today, is actually a number of meters different. So again, saying just I'm tied to WGS84, whether or not, is incomplete. You would have to say I'm tied to WGS84 G1674, and just so folks know, G stands for GPS week. So that means that that's when that realization of WGS84 was established. It's like an epic date, so it's as of GPS week 1674. Then there's other international frames, International Terrestrial Reference Frame, the International GNSS frame, and there have been a number of different realizations and epics of those as well. So just saying you were tied to ITRF wouldn't say a lot more about or include a lot more in that statement. So just slides on the international frame. Anytime that we're doing anything with GPS, everything is done in this international frame. Even if your data collectors are eventually giving you NAD83 coordinates, everything is done in this three-dimensional Earth-fixed, Earth-centered coordinate system, and then transformations are done after that in order to get down on to the North American datum frames. So if we look at the international frame, for instance, this is the IGS08 frame. What we can see here is that, and this is should be no surprise to folks, and each one of these are an established CORS station, continuously operating GPS reference station. As I said, it should be no surprise to anybody, but what we're seeing here to a great extent is plate tectonics, right? We're seeing this very systematic motion of the North American plate. You got California diving off to the east. That's they sort of do their own thing, right? And then we've also got this area of uplift vertically up in the northeast corner of Vermont, and that's due to isostatic adjustment. The Earth, or at least that part of the Earth, was covered with a mile and a half of glacial ice during the last ice age. It compressed the crust. The ice was removed, and now the Earth is still rebounding from the removal of that. And so you can also see down in Texas and Louisiana, you can see local subsidence, whether that be from loading on the Mississippi Delta or withdrawal of groundwater. There's some subsidence in California. So some of these things on the international frame are certainly associated with the North American plate, and other things are more localized. So what we're looking at today, so the WGM and or the international frame are basically aligned, and those today are about 2.2 meters offset from NAD83, or I should say really NAD83 is offset really from the international frame. Back in 1986, when NAD83 first came out, it was aligned to be the same as the international frame. Over time, we've gotten a better understanding of where that international frame is, or where the origin of that frame is. And so each of those WGS84s was another realization because they had a better idea of where the Earth's center of mass was. For mostly political reasons, we have left NAD83 alone, so that we haven't continuously changed it. Again, we're covering a distance of a couple of meters. So we've left that alone. So that's where we sit today, NAD83 versus where the rest of the world is. So vertically, and I think most folks are aware of this, we had the national vertical datum of 29. It was defined by holding 26 tide gauges fixed. Okay, there were some issues with doing that. One was that not all of them were on the same tidal datum epoch. And the other problem is that for anybody who knows much about sea level is truly a local phenomenon. So in one place is not the same as sea level somewhere else. And even moving a mile or two up and down the coast, sea level changes. So calling each one of those tide gauges 0 and then adjusting all of our leveling was probably not the best thing to do, but that's really all we could do at that point in time. So this sort of just shows where those tide gauges were across the country and Canada. Okay, so it respawned up with the north of 1988. It's defined by one benchmark up at, okay, which is up at the mouth of the St. Lawrence River. It's also the origin for the International Great Lakes datum. Okay, NAVD 88 is realized by over 500,000 marks in the ground. Right, so if and truly create and tie to NAVD 88, we have to go physically touch a benchmark, piece of brass, in order to the datum. A couple of problems with NAVD 88, right? So you or some things about that, right? Using one of these fixed heights removed that local mean sea level variation problem, right? Where not every tide gauge was actually truly 0. In a global sense, it was 0 locally, but not continentally. But the use of one fixed height did open up the possibility of unconstrained errors. So with leveling observations going across the country, without a station on the West Coast to adjust to, then there was no way to adjust out. So there was a buildup of these errors in our leveling. So where we stand today is we still have, as good as NAD83 and NAVD88 are, we do have some problems, right? As was seen on that cartoon showing the difference between ITRF 14 and NAD83. NAD83 is not as geocentric as it could be, right? We're off by 2.2 meters. And we don't really see that yet, but it's not going to be many years. But what you can walk out, go down to Walmart, buy a $99.99, buy a GNSS receiver that collects data from GPS, GLONASS, Galileo, Baidu, and you'll go out and you'll go to your backyard and you'll be able to observe, 50 or 60 GNSS satellites. Okay, at that point in time, you have the ability probably to position yourself in real time down a decimeter. So if I can position myself within the international frame to a decimeter, that 2.2 meters now shows up like a sore thumb. So this is a good opportunity for us to get ahead of that problem and fix the datums to where they should be prior to folks getting the ability to actually go out and do that. It's realized by passive control. Okay, and this is really one of the biggest problems, right? In order to really truly tie to NAVD88, you have to go out and touch a benchmark. And if those benchmarks are getting destroyed, disturbed, they're moving because of either they're subsiding up and down, or they're subsiding downward, right? Or up in the Northeast here or other parts of the country, there could be some areas of uplift. And the reality is there's probably a lot more motion that we just don't know about because we don't go to these benchmarks and re-level them. In many cases, they haven't been leveled since they were first set. So if I go out and find a benchmark, I'm taking it on faith that mark is in the exact same position that it was on the day that it was leveled some 40, 50, or 60 years ago, and that's probably not the case. Okay, so these are just to add some brevity. This is what we know about NAVD88 today, because to a great extent, because of that, the error in the leveling. We've got probably about a 1 meter tilt across the country from the east to west, and there's also about a half a meter bias from where that global sea level. Okay, so as good as NAVD88 is, there are physically some problems with that. So to address those problems, this is our plan. So first in 2008 and then updated in 2013, we've put out a couple of 10-year plans now that address this. And so our by 2022 to replace NAD83 and NAVD88. So we've put out 3 blueprints, which are on our website. Part 1 is the geometric, that's the horizontal aspect, latitudes, longitudes, and ellipsoidal heights. And here's how we're, this is how we're redefining frame. So we'll have 4 plate fixed frames. So the North American frame like we have today, and then we'll be covering the Pacific and the Caribbean and the Northern Marianas. We've defined the mathematical relationships. So for those who need to do transformations, that information will be available through this document. And then interframe velocity models. So being able to look at local motions within the coordinate system itself. So we currently have NAD83 2011 that covers North America. Also the PA11, which is the Pacific, and MA11, which is the Marianas. We're adding a new frame for the Caribbean. So the new frames now are the North American Terrestrial Reference Frame of 2022 NatRef. So that's what we're using here in CONUS. And then we have the corresponding frames for the Caribbean, the Pacific, and Mariana plates. Okay, part 2, blueprint part 2 is the geopotential or the vertical side of things. And we're starting out by using a global 3-dimensional geopotential model. So this means that where we're going with our new vertical frame is we're eliminating the need to use these benchmarks that we don't know if they are where they are supposed to be or not, and we're going to using GPS only for the definition of our datum. So we'll have a GNSS or GPS derived height from the NGS or the NOAA CORS network, and then we will be applying this global geopotential model that will then allow us to get our NAVD88, well, not NAVD88, but get the new heights in 2022. Okay, we'll have this graph talk about very briefly. High time dependencies. Again, time dependencies is the important part of this. If it marked this at a particular time and we continue to hold that, we know that things change, things move. So one of the things we have to do is to make sure that we account for these time dependencies in whatever models we put out. Okay, so we'll have to create a monitoring service for geoid heights or for geoid models to take into account things like deglaciation, right? I mean, as the glacier and their mass being redistributed around the planet through the ocean potentially has an effect on that gravity field, which is what we use for measuring heights. So under the names, so we had NAVD88, we had corresponding normal orthometric height datums for the islands and territories. So Puerto Rico vertical datum, Virgin Island vertical datum, American Samoa, Northern Marianas, Guam. So all of those height systems. International Great Lakes datum, which is a dynamic height system, different gravity datums, deflections, all of that on the left is being replaced with the North American Pacific Geopotential Datum of 2022, okay, or NAPGD 2022. So one can, and it's the truth that we will now have one vertical datum which connects everything on the left. So North American plate, Puerto Rico, Alaska, Virgin Islands, American Samoa, Guam, all of that now can be represented under one vertical datum. And that's the first time ever that we've been able to do that. Because remember, in order to actually get an NAVD 88 height in Guam, you would have to touch a benchmark, and the only NAVD, the nearest NAVD 88 benchmark, is somewhere in California. So, unless you could level across the ocean with with a level and a rod, you can't get NAVD 88 heights out in the Pacific. With this new datum, now we'll be able to get heights both on the mainland and anywhere in our territory, and we'll do this using the Geoid 2022 model. Right. So why replace? Number one, access. Right. It's find the sky than a 6-year-old benchmark. For anybody who's gone out to find a benchmark that hasn't been recovered lately, if you're in an area where a lot of those benchmarks were set along railroads, we know they turn into really nice rail trails, but unfortunately, a lot of those marks get destroyed in the process. And it's cheaper and easier. And in many cases, just as accurate to be able to use GPS today than it is to use more expensive and time-intensive methods like geodetic leveling. And the other thing is global standards. The rest of the world is going the same direction. We're working cooperatively with Canada and Mexico on the definition of these datums. Canada and the U.S. will be very tightly aligned on these new datums. For anybody who's done work along the U.S. and Canadian border and had to deal, especially with the vertical, horizontal's pretty well worked out. But if you've had to deal with vertical issues, you'll find that it's virtually impossible to represent the Canadian vertical datum CGVD, what was CGVD 28, to try to reconcile CGVD 20, whether they come from a survey or come from LiDAR, with NAVD 88 or even NGVD 29 heights. So this will help to resolve that issue along our international borders as well. So in order to do this, what we really need to do, better define our geoid model, and that this project NAVD is designed to do. It includes establishing or reestablishing a nation primarily through airborne methods. So if you're familiar with LiDAR, for instance, it's like a LiDAR project across the entire nation, but instead of flying with a laser, we're flying a relative gravimeter that allows us to measure changes in gravity while we're flying. Accessing the datums in the future will be, as I said, primarily through NSRS. So rather, instead of going out and finding a mark in the ground to base a survey on, either horizontally or vertically, it will be done most practically through the use of our course network. Secondary access could be used, or you could use passive marks, right? Benchmarks, or horizontal control points in the ground. You could use that as secondary access, knowing that there's no guarantee that those marks are where the published sites indicate that they are. So again, the idea is to get to being able to use a real-time type system, or at least the CORS network, where we monitor those stations daily. We know if they've moved, and we're able to account for all those motions so that your positions are always timely. Right? Why does this stuff matter? Okay? And I think it's important to remember that sometimes it seems like NGS is a little bit overboard, right, about what we're trying to do. But if you've got something underground, and I don't know, how accurate is it? Well, here's the coordinate. Well, is it plus or minus a centimeter? Is it plus or minus half a meter? Is a meter? The guy with the excavator digging really needs to know, right? So if we can represent our infrastructure, that's really what it was, right? And so that's it's important to all of our users. So if we look at NAD83 and look at NAD386, okay, so if you are putting out products, say NAD83, it implies those coordinates determined using these types of methods. Only after once you start saying NAD83 2007 or NAD83 2011 or maybe even NAD83 HARN do you even start to think about that those positions were established using methods of today, right? GPS type observations. So if I say I'm giving you NAD83 2000, NAD83 2011 coordinates, you're thinking immediately probably that they came through GPS. And the same goes with if I were to say, well, here's my NAD83 coordinates. Well, to me, that implies that this is okay. That may or may not be true, but that's what it says on the face of it. Right? So, whoops. Yeah, so the 86 network, okay, a whole bunch of triangulation. So a good example of that is here is a mark. It's in New Jersey, and it happens to have coordinates on it from actually prior to even going back to NAD 27. But what I've shown on here are 83 coordinates from the original NAD 83 86, which is down at the bottom of the screen, and then NAD 83 91, which is sort of an early HARN type number, and then up to the more modern NAD 83 2011s and NAD 83 2007s. And what we see is about a difference here of about 6 decimeters. So in this particular location with this particular mark, if I said NAD83, meaning any one of these, it could be, there's about a 6 decimeter error circle around that, right? So what this shows is as long as we know truly what those coordinates are, right? I mean, if I go back to this picture for a minute, right? If I said NAD83, it could have been any one of these, right? It could have been any one of these points could represent NAD83. But now if I apply a transformation, if I know which realization they are, okay, what I've done here is I've just taken all of those various NAD83 XX coordinates and transformed them to today's position. Then we can see that they all agree really at the sub-centimeter level, with the exception of the original NAD83 86 coordinate, which is the one down here, and that's only 2 centimeters different. Okay, so accurately knowing where these coordinates came from. Okay, think about this as a data layer in one of your surveys. If someone gives you NAD83, and that's all it says, right? NAD83 coordinates, how can you transfer, right? So we just saw that it could be anywhere in 6 decimeters and where it ends. But actually knowing exactly which coordinate frame it was relative to, we can nail that down to centimeter level if we want. And if we're talking about LiDAR projects and high resolution GIS data, centimeters now matter in our products. So when we're talking about performing transformations, right? I mean, you have to ask yourself these questions. And what I'm looking at here, is what I'm trying to think is, if you think about the data that you have in your shop today and how you're going to have to represent that or choose 2022, you need to know what your data is in today in order to accurately represent it in the new coordinate frames, right? And these are some of the questions that you have to ask. What's the spatial accuracy of your data today? What is it tied to now? are there temporal issues? Are you really sure you want to do this? So, what I recommend to folks is to start taking an inventory of your data, look at it and say, okay, what is it? What's its spatial accuracy, right? If its spatial accuracy is a meter, then it might be okay just to call it NAD83, and it might be okay to transform it to the 2022 datums in that sense, right? But if your spatial data, if the accuracy of your data is sub-meter, you probably really need to know where it came from and how that you can do the best job of transforming that data in the future. Okay. Ideally, you maintain your original survey data. I mean, that's what I encourage folks to do today, whether it be, survey data or GIS data. Don't just save the process contours, save the point cloud. That point cloud can always be reprocessed later relative to new geoid models, right? You can always, so rather than relying on a transformation, that data can actually be reprocessed. Right, and your metadata, make sure that we're including this datum and epoch and source. That information is going to help you to facilitate the transformations that you moving into the new frames. So here's some things that we can think about doing now, right? If you're not currently representing new data or collecting data, okay, collecting data in the newest coordinate frames, consider doing that. For within your area, if you have a survey shop, consider collecting precise ellipsoid heights on existing NAVD benchmarks. That's going to help us to do better vertical transformation model in your area. Move to NAVD88 if you're not already there. So if you can start moving your data and moving especially all of your newly collected data to NAVD88, that's going to help with transformation to NAPGD 2022. Okay, better understanding of the vertical conversion or the VertCon transformation model in your area. If you do survey work today and you're basing that on passive GPS or on passive marks in the ground, try to move away from that practice and start relying on GNSS and the NOAA CORS network as the basis of the control for all your projects. If you can be consistent in that manner, that's going to help all of your data to transform more smoothly. Okay. And again, require and provide complete metadata for all mapping contracts. Make sure that you're asking for the that you're going to need in the future. And if you're the one providing that data, that information, it's only going to help everybody as we move forward. So, and that brings us to our last topic, which is the new state plane coordinate system that goes along with this. So on our webpage, we have a page for state plane coordinates. You can look at policy and procedures notice that came out relative to our plans. We can look at some historical information on building the state plane coordinate system, and also initially laid out for both 2073. And the other thing, as we're starting to design default zones, and I'll show you a couple for New York, as we're starting to define these or design the default zones, those zones are available for folks to download. It's a image file, but it gives you an idea of what we're looking at for zone and what the distortions in that staging zone look like. So the federal register note came out that deadline has gone past, but the future deadlines are March 31st, 2020. We need these what we're calling requests and proposals. So a request means that a state is requesting NGS for a particular design, whether it be one that NGS has already designed as a default, or maybe a a request to NGS to design something state, and a proposal would be the state themselves, contractor for the state is going to create the zone. So the state would then make a proposal to NGS for what those designs might look like. Then March 31st, 2021 would be the deadline for the submittal of approved design. So if a state were designing their own zones, that's the date that they would need to submit the approved designs to NGS. So some things about the new state plane coordinate system. Essentially is going to be if left like NAD83. So when I say left alone, meaning that NGS's default designs will probably look very much like the state plane coordinate system for NAD83. It's going to consist of the Lambert conformal conic, transition Mercator, although you'll find that the oblique Mercator projection will probably be used a little more throughout the country than what it has been in the past. We'll look at that in a minute. So again, so our policy limited to those three projections. The zones are being designed to reduce distortion at the ground from NAD83 state plane. Those two state plane systems minimize at the ellipsoid. So state plane coordinates were designed to be no worse than 1 part in 10,000. These zones are going to be designed to actually be no 20,000 at the ground surface. Okay, so an improvement in the distortions. Defaults will be designed by NGS if no consensus input. And I forgot to put a slide in here, but consensus means that we have a series of stakeholders. Are the state surveying societies, the state GIS societies, the State Department of Transportation, and any university or college that has a geographic or geospatial program. Those 4 stakeholders must agree on what these zones look like. Okay, if there is not consensus, NGS will use our default designs. Okay, so if everybody in New York wants something different designing by default, all those 4 stakeholder groups have to agree. Okay, and if they do, then NGS will go along with what your recommendation is, as long as that meets our criteria. Let's see, limited. Yeah, I'm going to skip that. We're allowing a special use zone. So this is a different. So our new final policy procedure website, and these are a couple of changes that were made. So we're allowing the special use zone. So special use zone is the best example in the middle of the country. There's the Navajo Nation, which its land ownings cover 3 states, or go into 3 states in 5 different state plane zones. So we are saying that we will create a special use zone for the Navajo Nation. Okay, but again, it has to go across state boundaries. That's one of our criteria for that. NGS is designing a statewide zone for every state. So that means that New York, and I'll show you a picture of what that might look like. New York will have a single zone that covers the whole state. Okay, so think UT, but it'll be better. It's going to be designed to give you better performance at ground as opposed to the ellipsoid. We're also allowing a maximum of 3 layers. So this one statewide zone, okay, would be a single zone statewide, and up to 2 multi-zone. So for instance, you have 1 multi-zone right now. New York West, New York Central, New York East, and Long Island. So that's, for instance, that's one of those multi-zone layers. We might allow for another multi-zone layer, but that one would not be allowed to be statewide. It might be, if you think about out west, it might be a city or a county that's at a high elevation, so they may design a special zone for that area. But NAD27, oops, looks like here, so we can see, you know, the differences in the grid distance and the ellipsoid distance, where the ellipsoid to be, you know, either smaller or larger depending on where you are within the zone. Then, of course, if where we work, which is up at the ground, then we can see that those distances are quite different if we look at the gridded horizontal distance, right? Whether that be through orthophotography, or orthophotography, generally speaking, is that it's at a grid projection, but what one might measure on the ground would be different. Okay, and of course that's going to change with your elevations and where you are within the zone. So NGS's approach to this is to move our plane, if you want to plane, the terrestrial surface rather than the ellipsoid surface. So we can see here now that our grid distance is approximately equal to what our ground distance would be. Okay, and at 2 points in this zone, that grid distance is actually equal to that point. Okay, or at a particular point. So if we take this as a start to our approach, and then move our axis, okay, we change the projection axis. Now we're looking at a plane that sort of is the average of some of our terrain, where now we have many points along that zone, or along that plane, that provide a one-to-one correspondence between grid distances and ground distances. We have a much better representation and a better or a lower distortion between the grid distance and a horizontally measured distance. Okay. So the last couple of minutes here, I'm just going to show you what we're looking at for zone. This is your east zone. Okay, NAD83, and we can look at the distortion. So through the central part of the state, we're looking at you know, a negative, you know, 160 parts per million through there. If we look at redesigning the zone, okay, one thing we did is we changed the location of the central meridian, but we've also moved it so that we're trying to represent distortions at ground level as opposed to the ellipsoid. And we see that now that the distortions are much lower in the central part. We're looking more in the minus 100 per million. And now out on the east west, like going Albany and Troy, we're actually down at plus or minus parts per million. So we've significantly increased or decreased the distortion in that area. This is our current New York Long Island zone. So this is the Lambert zone. One thing I didn't really talk about was we're changing the Lambert from a 2 parallel definition to a single parallel definition in the future. So one idea that we have here, and because of the relief and the elevation on Long Island, Long Island's already a pretty low distortion zone. Most of it here is plus or minus 5 parts per million through the great majority of the land. This is one of the ideas that we are floating for a Long Island zone. So this would be a obliquator projection that would put the origin or the central at a skew azimuth of plus 25 degrees. And that allows us then to take the zone both that 5 parts per minute also increases accuracy at some of the extents of the zone. When we look at statewide zones, this is what you currently have. This is what UTM Zone 19 looks like for New York, which would actually cover the state. And you can see that most of the central part of the state, or the eastern part of the state from Syracuse east, is plus or minus about a minus 600, minus 500 parts per million. If we were to change this to a Lambert conformal contact reaction, okay, we've increased that to a lot more of the population. So more of the population of the state has a lower distortion on statewide. And obviously, I think folks understand why the statewide zone, surveyors could use it, but predominantly statewide zone is being built with the eye towards the GIS community, so that there's one single statewide zone that mapping can be done in. There are a number of states that even Vermont, lucky for instance, they're small enough to have a single zone, but there are a lot of states that don't have a single zone. Even a UTM projection doesn't cover the entire state. There might be a between two projections or two UTM zones that go across the state. So even Texas and Alaska will have one single zone that all work could be represented. So that's what I had for you today. My contact information is there, and I'll get back in touch with Colin, obviously, because if we need to figure out a way to do this, if it didn't work for people, my sincere apologies. I saw somebody said bandwidth is always an issue, so you never know what's going to happen. But my contact information is here. It's available on the NGS website, and so feel free to reach out to me. Let me open this up. I didn't ask you, Colin, but slide deck. I know that this, of course, actually, I guess this is going to be up on your YouTube site, but if it's got problems with the recording, then that may not work out so well anyway. I will be posting this presentation at that link on my website. So if anybody wants to grab it there, you'll probably be able to see it in probably within about a week or so. Sorry, I'm just trying to read down through the. Yeah, it doesn't look like there's, well, if there were questions, it doesn't look like there are any specific questions. So feel free to hit me up directly with either a phone call or email. And we'll take it from there. Yeah, Colin, give me a call afterwards. Give me a call on my cell phone, and we'll talk about this. Try to set up some feature. All right. Thanks, everybody.